Okay, so now with the idea about basic solutions, let's go further and define something called basic feasible solutions and keep on our connection between these with those extreme points. So we have a lot of basic solutions. Among them, some are feasible, right? We know there are two sets of constraints, ax equals b and x non-negative. By the definition of basic solutions, these equality constraints are definitely satisfied. So if one also satisfies those non-negativity constraints, it will be a feasible solution. So we define basic feasible solutions in the following way. A basic feasible solution to a standard form linear program is a basic solution if all the basic variables are non-negative. We know basic variables are obtained by solving ax equals b. Okay, so we cannot predict whether the variable will be negative, positive, or zero. So in some cases, there may be negative basic variables. Then that's infeasible. Okay, if that does not happen, then it's a basic feasible solution. So this was our previous example. If we give you these 6 basic solutions, it's very easy to determine which of them are basic, which of them are not. Because you have these two negative numbers, we know these two are not basic feasible solutions. Okay, but the other 4, they are basic feasible solutions because all the basic variables are non-negative. Okay, that's the idea. So why basic feasible solutions are important? Because they are exactly extreme points. So for a standard form linear program, a solution is an extreme point of the feasible solution, of the feasible region, if and only if it is a basic feasible solution to that linear program. So if it is a feasible solution, if it is an extreme point, then it is a basic feasible solution. Or if it is a basic feasible solution, it is an extreme point. And we're not going to prove this, and we only hope that you can keep that in mind, memorize this. However, one thing we will do is that we will use graphs to give you some intuition. And I hope that this intuition can help me convince you that this connection is indeed. So we want to show that there is a one-to-one mapping between BFS and the extreme points. For example, for the previous example, we know there are 4 4 basic feasible solutions. And then on the graph, we can see where they are. So for example, for point A, we can see that x3, x4, they are slack, so they doesn't really convert back to the original problem. In the original problem, the 2 variables are 2, 2, and that's exactly where we can find the point A. The point A is indeed one extreme point of the feasible region. For example, point E. Point E, the basis includes x2 and x4. And we can see that x2 and x4, they are positive. But for the original formulation, we only have x1, x2, right? So 0, 3 is our point E, and so on and so on. We can see that the 4 basic feasible solutions corresponds to the 4 extreme points of the feasible region. Or this is our another example, right? In this case, we may still find the one-to-one correspondence. For these 3 points, they together give us one basic feasible solution, right? And that's why they give us one extreme point, 6, 0, 6, 0 here. Okay, so this is not feasible. For this one, it's 0, 3. 0, 3 is here. And then finally, for this one, this is 0, 0 is here. Okay, so again, basic feasible solutions are just extreme points. So what's the implication of that? Now we can say that basic feasible solutions are highly related to the optimality of linear programs. Given any linear program in standard form, if there is an optimal solution, then there is an optimal basic feasible solution. Why? Because we know if there is a solution, an optimal solution, there is an extreme point optimal solution. Also, extreme points are just basic feasible solutions, so now we only need to care about basic feasible solutions. So our strategy may be the following: to find an optimal solution. Now I do not want to search among all extreme points. I want to search among all basic feasible solutions. Among them, I find the best one. If there is an optimal solution, that's the optimal solution. But we know that these two sets are equally large. So searching among this set and searching among that set seems to be the same. However, from the perspective of using computers, they are definitely different. Think about the definition of extreme points. A point is an extreme point if you cannot find a line segment such that the two endpoints are in the set and that line segment contains the point, or something like that. If they do not exist, it would be very difficult to write a computer program to verify whether a solution is an extreme point, right? Or think about that by yourself for a while, you will realize it. If I ask you to write a program to detect whether a point is an extreme point of a given set, that would be difficult, because it's hard for you to enumerate all possibilities of those line segments. But if I give you a solution, okay, a basic solution with several numbers, and I give you a standard form, then verifying whether it is basic feasible is easy, right? If you want to write a program, that can be done in a short time, because all you need to do is to check the number of zeros and the satisfiability of whether it satisfies those equality constraints and the non-negativity. Easy. So, because we will do a lot of calculations, we will focus on basic feasible solutions instead of extreme points. Because basic feasible solutions allow us to develop clear algorithm with algebra, okay? And we're going to see what's going to do that in the later videos. But one thing to keep in mind is that we use basic feasible solution because we need to use algebra to solve general problems, to solve general multi-dimensional problems. So if now I give you a task is to enumerating all the basic feasible solutions, now you know it's possible. If I give you a standard form LP, ask you to enumerate all the extreme points, it will be hard. But enumerating all the basic feasible solutions would be possible. You may write a program to do that. So now we are closer to solve a general linear program. One possible way is to enumerate all the basic feasible solutions, and then we may find a best one. Unfortunately, it would be too time-consuming. Okay, if you have n variables and m constraints, we know we have at most n choose m basic feasible solutions. Just convince yourself that if n and m are both very large, then this number can go to a very large scale, and listing all of them would take too much time. If you know something about complexity of algorithms or whatever, you know big O n choose m is roughly big O n factorial. And that means if we want to enumerate all the basic feasible solutions, that would take an exponential time in the worst case. Okay? So that's not really possible, or I should say that's not really practical. So instead of doing that, we need to improve the search procedure. Essentially, we hope that we do not need to look at all the basic feasible solutions. Instead, we want to know something more about basic feasible solutions, and in particular how they are connected. Okay, so let's define adjacent basic feasible solutions. Two basic feasible solutions may be adjacent or not. So let's see this. Two bases are adjacent if there is only one variable that is different, okay? And the two basic feasible solutions are adjacent if their associated bases are adjacent. So think about the first one. When we choose a basis, we choose several columns, right? So for two bases, there are two sets of columns. If all the columns are identical but one column is different, then we say they are adjacent. That's the idea. So for example, if I give you two bases like this, x1, x2, and x1, x4, then they are definitely adjacent because only one variable is different. If I give you x1, x2, and x3, x4, then they are not adjacent because two variables are different. Okay? How about x1, x2, and x2, x4? They are adjacent because we know sets are, the order does not matter. Okay? So x2 is the same, but x1 changes to x4. So a pair of adjacent basic feasible solutions certainly corresponds to a pair of adjacent extreme points. That means extreme points that are on the same edge, okay, intuitively. So switching from a basis to its adjacent BFS is to move along an edge on the feasible region. For example, here, so again that example, if we want to switch from x3, x4 to x1, x3, okay, we change one variable. We change one basic variable. Then what's happening is that we move from this extreme point to an adjacent extreme point. Okay? Adjacent BFS corresponds to adjacent extreme points. Okay? Changing one variable means to move to an adjacent basic feasible adjacent extreme point along an edge. Okay? So let me give you a three-dimensional example. Suppose I have this problem. Okay, we know the objective function doesn't matter, but for constraints, suppose that in this three-dimensional space, I have three constraints like this, and I may convert them into equalities by adding legs. In that case, each basis must have three variables. Why? Because there are three constraints, equality constraints. For example, if I choose x4, 5, 6 as my basic variables, then for x1, x2, x3, they would all be 0. Okay, because the basis is here, and these three are non-basic variables. So here I only list 8 values. 8 points, because these 8 points are feasible. Only these 8 points are feasible. And you may check that these are just these 8 corners or extreme points of this feasible region. Okay? So here the idea is to explain the concept of adjacent BFS or adjacent extreme points. So let's take an example. Suppose I'm looking at A and how about C? Okay, A and C. From the figure, we can see that they are not adjacent. Okay, so let's see whether they are indeed not adjacent. Oh, indeed, because x4 and x5 becomes x1 and x2. Two variables are different. So what? Oh, so they are not adjacent, just as what we see on the figure. How about G and H? G and H. We can see that x2 and x3 are the same, and only x1 and x4 are different. Okay, only one variable is different. When I say this, that means from G to H, only one variable changes. Okay, so from G to H, we move along an edge, and to get an adjacent basic feasible solution. Okay, so now, given all these ideas, we now only want to do the following. Given any basic feasible solution, I want to move to an adjacent one that is better. Okay, instead of searching for all the BFS, I only want to do a somewhat greedy search. At a point, I want to do some improvements, and then I do an improvement, and then I do an improvement again, and again. I don't really need to check all the solutions, right? I only want to check better solutions. And if at a solution there is no improving directions, that means all its neighbors are worse than itself or equally good. What does that mean? That means that BFS is optimal, right? If I am at a solution and all the neighbors are worse than me, then in this linear program, that just means this solution is optimal, right? So with this idea, we have just introduced the central heart and central idea of simplex method. Next, we will introduce the method in details. First, with the geometry or intuition or concept, and then about algebra. How do we really calculate all the procedures we need? How do we do improvements, and to see how this idea is implemented. Thank you.